Welcome back to our online classes, and in today's class we are going to look at adiabatic process. Adiabatic process is a thermodynamic process in which there is no exchange of heat between the system and the surrounding, and that makes Q to be equal to 0. If Q is equal to 0, you are asking yourself, how is work being done? Because for work to be done, we need Q to be present. So the work done in adiabatic process is because of the internal energy of the system. So the internal energy of the system is the one responsible for the work done in adiabatic process. That's going to make us to look at the relationship between temperature and volume, temperature versus volume, and also pressure versus volume. Because in a adiabatic process, there's a change in volume, temperature, and pressure. And from that, then, we can look the relationship between these three: temperature versus volume, pressure versus volume. According to the first law of thermodynamics, change in internal energy is equal to Q minus W. And because Q is equal to 0, we can then write delta U is equal to 0 minus W, making delta U to be equal to minus W. And this we can then say work done is equal to minus change in internal energy. Because you can see when the internal energy is doing work in a adiabatic process, is going to go down. It's going to go down because it's the one making the gas to expand adiabatically. This is the same as saying the internal energy of adiabatic process is the same as NCV dt, and we still maintain our minus. This is the same as NCV dt. What is work done? We have seen work done. Work done is equal to minus P dV, and we can take this on the left hand side to replace it with W and say P dV is equal to minus NCV dt. Because these changes takes place at a very short time, it means that instead of writing this equation this way, we can proceed and write it. Because the changes are very small, so we can say P dV is equal to minus NC dt. From ideal gas equation of a perfect gas or ideal gas, pressure PV is equal to nRT, and we can write then in terms of pressure that pressure is equal to nRT over V. We can then replace this term here with this pressure here and say nRT over V is equal to, or dV is equal to minus nRT dt. So number of moles are common, so we can cancel them, leaving us with RT over V. dV is equal to minus CV dt. Okay, so we can still write this as RT over V. dV is equal to minus C dt. So we can bring this T this side, and that's going to make us with R dV over V is equal to minus CV dt over T. And we can equate this to 0 and then say R dV over V plus CV dt over T is equal to 0. So if you look at it now, we can integrate it. We can integrate dt and dv, and that's gonna be R. If you integrate it, you're gonna have R ln V plus CV ln T is equal to 0. And of course, we can write it in terms of a constant. R ln V plus constant plus CV ln T plus constant is equal to a constant, and then we can is equal to 0, and then we can take constant to the other side and write it as R ln V plus C V ln T is equal to constant. Okay, so we have R and we have CV. There's a relationship between R and CV because we have Cp, molar constant heat capacity at constant pressure, minus CV, which is the molar heat capacity at a constant volume, is equal to R. So we can then rewrite this as R is equal to Cp minus CV. So instead of writing R here, we can replace R with this term here and write it as Cp minus CV ln V plus CV ln T is equal to C. And we can divide both sides by CV, we can divide both sides by CV, and because this is a constant, we can divide by this constant, and this can be rewritten as Cp over CV minus CV over CV ln V plus CV over CV ln T is equal to constant. Constant divided by constant is constant. So this one can cancel each other, and this one will be cancel each other. This is the one. So in adiabatic process, we have what is called adiabatic index, or the ratio between the Cp and Cv, or molar heat capacity at a constant pressure and molar heat capacity at a constant volume, and this one is what we call adiabatic index, or gamma, represented as gamma, which is equal to Cp over Cv. So we, instead of writing Cp over Cv, we can write it as gamma, and that's gonna make this one here, this equation will change to be, we can then rewrite this equation to be gamma minus, because Cv divided by Cv is minus 1, okay, ln V plus ln T is equal to C. So according to laws of natural logarithms, math 1, and then you can rewrite this as ln V to the power gamma minus 1 plus ln T is equal to C. Okay, so this is ln V and ln T, so that's the sum of two natural logarithms, can be written as the product of the two. So that one, we can rewrite this one here as ln TV to the power gamma minus 1 is equal to C, and then you can write this as TV to the power gamma minus 1 is equal to C. So this is the equation that we are having. So assume that we have it at different temperatures, or from T1 to T2, or initial temperature to final temperature, initial volume to final volume. We can then write it as T1 V1 to the power gamma minus 1 is equal to T2 V2 to the power gamma minus 1. Okay, so this is the relationship between temperature and volume in adiabatic process. We are going to see this in equation, we're going to see this in practice, and therefore most of the time they ask students, or you can know at what was the final temperature in which the work was done completely, okay, or what was the final temperature. From here you can find the final temperature as T2 will be the ratio of V1 over Vf times T1 to the power gamma minus 1. Okay, so this is the relationship between temperature and volume. So let's look at the relationship between pressure and volume in adiabatic process, because we did say there are three things here: temperature, there's change in temperature, change in volume, and also change in pressure. Okay, So we can then write back from the previous slide V1 or T1 V1 to the power gamma minus 1 is equal to T2 V2 to the power gamma minus 1. So let's look at this at different pressures. Let's say P1 and V1 or P1 and P2. So from ideal gas equation, I'll put this in bracket. From ideal gas equation, we know pressure PV is equal to nRT. So we want to relate pressure and volume, so we'll write it here as pressure and volume relationship. We want to see how these things are related relationships. Okay, so because we want to look at pressure volume relationship at different temperature, then we can divide both sides by nr. Divide both sides by nr to make our T is equal to PV over N over nr. So if we're looking at T at, let's say, initial temperature, then you can go back to this our equation which says T1 V1 to the power gamma minus 1 is equal to T2 V2 to the power gamma minus 1. So we can replace, in case of T1, we can replace every T1 by this part here, by this equation here, and say at P1, at T1 we'll have P1 V1 to the V, this one V1 to the power gamma minus 1, everything over n r is equal to, at final temperature, then you can have P2 V2, this P2 V2 is from this equation, times V2, this one here, V2 to the power gamma minus 1 over nr. N is constant, we assume that is 1. It is not a constant, as we assume it is 1, but r is a constant, so they can cancel each other, and that will leave us with P1 V1 to the power gamma minus 1 is equal to P2 V2 to the power gamma minus 1. According to, this is exponent, this V is to the exponent gamma minus 1, the same as the one on the right, and therefore this is V and this is V, they have the same base, so meaning this is like exponent 1, and we can rewrite it as, so according to law of natural logarithm, exponent times, these are times product, so 1 times gamma to minus 1 is the same as times, is the same as addition, so we can write this as P, because V and V is equal to the same, so we can write V1 to the power gamma minus 1 plus 1. This plus 1 is the exponent of this V, because they have the same base. This volume and this volume have the same base, and this can be equivalent to P2 V2 to the power gamma minus 1 plus 1. The same on the right hand side equation, and this one will leave us with P1 V1 minus gamma minus 1 plus 1 is equal to 0, so it's going to leave us with gamma, and this is the same as P2 V2 to the power gamma minus 1 plus 1 is equal to 0, and then finally we can say that P1 V1 to the power gamma is equal to P2 V2 to the power gamma. So in this is the relationship between pressure and volume. So it means that we can know our initial pressure, our initial volume, and final volume, but then we need to ask ourselves what is the final pressure in which the system stops working. In that case, we can then rewrite this in terms of pressures, final pressure, and then say that our P2, if we know our initial pressure, initial volume, and final volume, then we can look at P2 and rewrite this equation as P2 is equal to the ratio of V1 over V2 times P1 to the power gamma. Okay, so here are two different equations that you must know how to use them. The first equation we say T1 V1 to the power gamma minus 1 is equal to T2 V2 to the power gamma minus 1, and we wrote it in terms of assume that we know our initial volume, initial temperature, and final volume. We can then look at final temperature, meaning that T2 will be the ratio of V1 over V2 times T1 to the power gamma minus 1. So we can use this equation to determine at the temperature, final temperature. But the most important thing is to know the value of gamma. What is gamma? We have said that gamma is equal to the ratio of Cp, or molar constant heat capacity at a constant pressure, over molar heat capacity at a constant volume. So Cp over Cv, that's the value of gamma. This value of gamma differs due to types of gases. We can have monoatomic gases, diatomic gases, and polyatomic gases. Remember, these monoatomic gases, diatomic gases, or these types of gases have different degrees of freedom. And for example, for monoatomic gas, I write monoatomic gas. So we have Cv and we have Cp. So for monoatomic gas, especially, they have 3 translational motions. So it will be 3. It will be 3 times 1 over 2 R. That's going to give us 3 over 2 R. And the Cp will be 5 over 2 R. And for diatomic, their Cv is 5 over 2R because there are 5 degrees of freedom, 3 translational and 2 rotational. And for their Cp will be 7 over 2R. So now let's look gamma, the value of gamma for monoatomic gas. So let's say monoatomic gas like argon, okay? Its gamma will be Cp over Cv, and that's going to Cp of monoatomic gas is 5 over 2R divided by 3 over 2R. So R and R can cancel each other, and this is going to leave us with the value of gamma to be, gamma is equal to 5 over 2. When we divide, it's going to be 2 over 3. So 2 cancel 2, and we are going to have 5 over 3. So the value of gamma for monoatomic gas is 5 over 3. So if you are to substitute it in this equation here, then you can say that it is T2 is equal to the ratio of V1 over V2 times 5 over 3, which is the value of gamma, minus 1 times T1. Let's proceed in the final slide, the next slide. So we have seen that we proceed in our last example. We did see gamma for monoatomic gas is 5 over 3, and if we are to look at the difference between gamma minus 1 is going to be 5 over 3 minus 1, and that's going to give us the least common number here is 3. So if you put here 1, 3 goes into 3 once. 1 times 5 is 5, minus 1 goes into 3. 3 times 1 is 3, and this is going to give us a value of 2 over 3. So it means that if we are to find the final temperature, we're going to say T2 is equal to the ratio of V1 over V2 raised to the power 2 over 3 times T1. I'm repeating, this 2 over 3, let me write it properly, is the difference between gamma minus 1 for monoatomic gas. And for diatomic gas, diatomic gas gamma is equal to Cp over Cv, and that's going to be 7 over 2 over 5 over 2, and that will be 7 over 2 times 2 over 5, so it's going to be 7 over 5 minus 1, and that's going to be here 1, then 5 goes here 1, it's going to be 7, and then 1 goes here 5 times 1 is 5, so it's going to be 2 over 5. So it means that for diatomic gas, the value here, that gamma minus 1 is equal to 2 over 5, and 2 over 5 is like 0.4. It's like 0.4. So let's assume that our initial volume, let's say given that V1 is equal to 2.5 liters and V2 is equal to, let's say, 4.1 liters, and T1 is equal to 296 Kelvin, and it is monoatomic gas, and we are given that it is our gas. The gas here is equal to, let's say, argon gas. So it means it's monoatomic gas. Also, you need to know these types of gases. Is it the name of the gas? Is it mono, di, or tri? You must know the examples of those type of gases. So in this case, we can substitute to look for T2, and we can ask ourselves T2 is equal to how many? We are going to see. So we can substitute and say T2 is equal to the ratio of V1, and V1 is 2.5. 2.5 over V2 is equal to 4.1. 4.1 to the power, and you have been told it's argon, and you have looked that it is equal to gamma minus 1 times T1, and that's going to be 2.5 over 4.1 raised to the power 2 over 3 times T1, which is 296, and that's going to give us a value of, let's do it quick, 2.5 divided by 4.1, okay, raised to power 2 over 3 over 3 times 296, and that's giving us 212. That's going to give us 212 Kelvin. Okay, so T2C. And this one can make sense because in adiabatic process we expect final temperature to be of a lower value compared to initial temperature. Okay, because as the work is being done, the temperature decreases, the internal energy decreases. So this is all about what you need to know. And for pressure, we have said P1, V1 to the power gamma is equal to P2, V2 to the power gamma, and therefore we can relate P2. If we know all other parameters, we can say P2 is the ratio of V1 over V2 to the power gamma times P1. Here we take gamma straight. If it is monoatomic, meaning that gamma is equal to Cp over Cv, and Cp is equal to 5 over 2 divided by 3 over 2, and that's going to be 5 over 2 times 2 over 3. Let's cancel each other. It's going to be 5 over 3, and 5 over 3, and 5 over 3 is the same as 5 divided by 3. It's the same as 1.67. So this is the same as P2 is equal to, let's use the same values here. Just let's write equation V1 over V2 to the power 1.67 times P1, and that's going to give you the value of P2. Okay, so let's do it. 5 divided by 3, it gives us that value. So now you need to know the type of gases that you're working with, if it is diatomic or monoatomic gas, and or it is polyatomic gas. So I hope This one has made sense, so you can try to solve those questions. There's sometimes you will see that TF, T2 or final temperature is equal to the ratio of initial volume and final volume times T1, and this raised to power 1 over C. If you find this one here, 1 over C, you are going to find the same value like if you were to look for the gamma, depending, so meaning that the type of gases must be the same for the value to be the same. For example, let's just look this. We know that C is equal to Cm or Cv over R, and let's take for monoatomic gas. For monoatomic gas, Cv is equal to 3 over 2 R over R over R, so R will cancel R, so we're going to remain with C is equal to 3 over 2. Okay, so 3 over 2, so we're going to put this one because it is 1 over C, it's the same as 1 over 3 over 2, and that's going to be 2 over 3. And then you can see this one is the same as this guy here, is the same as this guy here. So if we can relate at the end, can I write here? Yes, I can write here. So we can relate that T1 over Tf is equal to Vi over Vf to the power 1 over C is equal to Vf. Actually, this should be Vf to V1 is equal to Vf over V1 to the power gamma. So this is the relationship between those two. What I'm trying to say is that once you find this value here, gamma minus 1, you will find it, like for example, monoatomic gas is 2 over 3, and if you find this 1 over C for monoatomic gas, you will still find 2 over 3. And if you were to draw a sketch of diagram or PV diagram or adiabat, then you can realize that it goes like this, or let's say something like this. So if this is our initial temperature, our final temperature will be here, and this will be our initial volume, and this is going to be our final volume. Okay, so yeah, there's no space, but yeah, at least share with your friends, like and subscribe. If you have not subscribed, subscribe, and welcome back to our viewers who have subscribed, and for our new viewers, welcome and be part of Bilton University. Thank you so much. Goodbye.